What does it mean when it seems like a comet is breathing? This mysterious image, evoking thoughts of a living creature, simultaneously amazes and interests scientists and space enthusiasts. At the center of this enigma is an interstellar traveler named Tria Atlas, which, like a living organism, ejects something astonishing into the silent icy void, 40 kilograms of water every second. How far is this emptiness from the sunlight and warmth needed to sustain such behavior? The questions that arise among astronomers seem almost supernatural. While it is beyond the zone where solar rays can easily warm and cause evaporation, it continues to emit such a significant flow of water. Experts whisper among themselves, it behaves like a living organism. But what exactly is hidden behind such unusual activity? The story of this comet is not limited to just this fact. Its composition reveals strange compounds, nickel without iron, cyanides in its tail, as well as rumors that the origin of this celestial body may date back to eras far preceding the formation of our own solar system. Perhaps it is billions of years older than us. While these mysterious details excite scientists' minds, away from this interstellar guest, researchers are encountering unique radio signals, considered the largest and most unusual recorded to date. In October, a series of strange formations appears in the sky, resembling radio groups, raising questions about a possible connection with the mysterious three-eyed object known as Atlas. Recently, a new generation spacecraft launched by Blue Origin sparked more questions than answers. Was it just another flight, or are there deeper secrets behind it? Were these events connected in any way? Stay with us until the very end as we attempt to unravel all these mysteries, because only then can we understand what is happening in our cosmos. In this new storytelling format, which combines several plotlines, we will keep you updated on all news related to space and what is happening in our sky. If these mysteries have touched you as deeply as they have me, don't forget to leave your feedback so you won't miss any important updates. As events unfold in real time, leave comments sharing where you're following our news from, what time it is for you, and whether you believe we can uncover the full truth about these discoveries that could change our world. And if you want to support the development of this community, share this information on social media, whether X, Facebook, Reddit, or in your group chats. It is thanks to your support that we can continue exploring such amazing stories. So, thank you for your help and trust. The first part of our story is The Impossible Signal, Part 2 of 43. Imagine yourself drifting in the cold, silent darkness of space, more than 3 times farther from the sun than our Earth. Here, sunlight barely reaches, and everything around seems immersed in eternal darkness. The ice covering everything remains frozen forever, and comets appear to freeze in place, losing all activity. Everything around seems to be in a state of sleep, awaiting a new wave of cosmic events. Suddenly, amidst this gloom and silence, you notice something truly astonishing. It's not just a comet, it seems to be a living creature, ejecting 40 kilograms of water into the silent void every second. Not a small stream, but a powerful flow bursting from its icy body, as if trying to rid itself of something very important. This interstellar comet, named Tria Atlas, has come to us from the depths of space, from other systems, bringing with it rules that clearly differ from those governing our solar system. All of this seems incredible, and the first clues came with the help of space telescopes. Imagine a situation that, in essence, resembles something astonishing and highly unusual. This comparison is as striking as if, every minute, a volume of water equal to that of a small car were ejected into the infinite cosmos. Such is the scale of the flow emanating from this mysterious comet, orbiting very far away. The distance at which these objects are located is so vast that they can barely be heard or noticed. Like a quiet whisper in the endless silence of space, where even the brightest comets die without reaching the warmth of the sun. At such a distance from the sun, these icy bodies remain in a state of freezing and dormancy, almost dead, devoid of activity and energy. For their water ice to sublimate, that is, transition directly from solid to gas, bypassing melting, heat is necessary. And here, in the depths of space, there simply isn't enough to activate the processes that make a comet truly alive. Under these conditions, comets wait until they approach the Sun closely enough for its warmth to awaken their internal reserves. Then they begin ejecting streams of gas and dust into space, creating the bright tails we are accustomed to seeing in astronomical observations. However, in contrast, three astronomical objects known as the 3 Atlas did not receive such instructions. They behave completely differently. Perhaps you remember the first confirmed interstellar visitor, an object dubbed Oumuamua. It was dry, like a bone, with no hint of water or gas emissions, just a falling stone rushing through our region of space, quiet and motionless. Its appearance was unusual but predictable. After all, it was just a celestial body, not behaving differently from our familiar comets. After this, a second interstellar comet appeared, known as Borisov. Part 3 of 43. This object was active, but all its actions were strictly according to a script. It resembled a standard comet, which, despite its interstellar nature, behaves just like any other, ejecting dust and gas, leaving behind a characteristic tail. In such a situation, everything seemed predictable and did not evoke much surprise or excitement. But everything changed dramatically with the appearance of an object called 3 Atlas. This comet is something entirely different. It seemed to come alive, somehow transcending the usual laws of nature. It ejects water into space with a roar, whereas in normal circumstances, these regions are completely silent. This fact raises an important question that concerns every astronomer aiming their telescope at this mysterious body. How is this possible? What mechanism, what unusual phenomenon, or what internal secret could explain such activity? Perhaps there are some rare and exotic types of ice that we have yet to discover, ones that sublimate at temperatures much lower than those considered typical for standard water ice. Maybe the core of this comet is still warm, despite billions of years having passed since its formation, and processes are occurring inside that we do not yet understand. Perhaps it rotates in some peculiar way, focusing sunlight into hidden reservoirs of volatile substances, or chemical reactions are taking place within the rock that previously remained a mystery to us. Water is just the beginning. Spectroscopic data obtained from 3 Atlas reveal even more astonishing facts. Its composition includes cyanide, nickel, carbon dioxide, all in concentrations that seem illogical or impossible within the framework of conventional models. Every new observation adds another layer to this complex puzzle, turning each spectral signal into a potential key to understanding. Each detected line is like a question without an answer, filling scientists with new hypotheses. In the modern era of astronomy, we have a rich arsenal of tools that allow us to observe and analyze various aspects of cosmic objects. Among them are spectroscopy, photometry, and polarimetry, three powerful methods that serve as windows into the depths of the universe. These tools enable us to see the tiniest details and characteristics of objects, as well as draw important conclusions about their composition and nature. It is no coincidence that having three such atlases is not just curiosity or a peculiar feature. It is a kind of key that unlocks access to new knowledge. These atlases are like a crack in our understanding of the cosmos, through which we can glimpse the amazing and sometimes mysterious processes occurring within it. Through such a crack, we are able to see something unusual and astonishing that goes beyond our usual ideas. Part 4 of 43. The second part of our story is dedicated to the mystery of nickel without iron, an unusual and astonishing discovery that prompts us to consider the complex processes occurring in space. It is believed that comets, like many other celestial bodies, follow certain patterns in their behavior. When they approach the Sun and begin to heat up, various metals start to evaporate from their surfaces. In this process, iron and nickel, two metals commonly found together in meteorites and cosmic objects, appear simultaneously, as if they are old trusted friends who always travel together. Their appearance is one of those cosmic constants that astronomers rely on when drawing conclusions about the composition of comets and asteroids. But suddenly, something unusual happens. Large telescopes, such as a very powerful and modern one located in Chile, direct their spectrographs at one of these objects and detect something completely unexpected. Instead of the usual iron lines in the spectrum, bright lines of nickel shine through, indicating that this metal is abundant, while iron is either absent or so weakly expressed that it is barely noticeable. This phenomenon, nickel without iron, is like finding smoke without fire or footprints without a trail, raising many questions among researchers and leaving them puzzled. If we consider our own solar system, such a phenomenon seems impossible. When a comet heats up enough to release metals, iron and nickel usually appear together because they are part of the same minerals formed under similar conditions. During their formation, sublimation, and evaporation, these metals remain bonded to each other. Therefore, their simultaneous release and presence in comparable proportions is a standard phenomenon we are accustomed to observing. However, in the case of this Tria Atlas, it appears as if a different picture has formed, creating the impression that these metals appeared independently of each other, under special conditions that differ from the usual. At a distance of about 2 1/8 astronomical units from the Sun, scientists recorded a nickel outflow from a comet at a speed of approximately 5 grams per second. This may seem like a small amount, easy to underestimate until one realizes that this figure is not an exception but a constant process. And it occurs continuously, second by second, while iron, surprisingly, is not visible in this process. This is not a glitch or a malfunction of the instruments. It is a pattern that indicates something important and fundamental. This is how the comet reveals its composition, how it is structured. Various scientific hypotheses have been proposed to explain this unusual phenomenon, but none seem entirely convincing or straightforward. The first hypothesis suggests that, in the environment where this triatom was formed, nickel may have been part of volatile compounds that easily evaporate at relatively low temperatures, while iron was incorporated into more refractory minerals requiring much higher temperatures to vaporize. Imagine nickel as a traveler, accompanying the volatile ices. Over millions and billions of years, interstellar objects are constantly and intensely bombarded by cosmic rays and ultraviolet radiation, which strike their surfaces with incredible force and duration. Such prolonged and harsh exposure to cosmic factors can uniquely and sometimes unexpectedly alter the chemical composition and structure of these bodies. As a result of radiation processing, a special layer rich in nickel may form on the surface, while the iron within it either sinks deeper inside or undergoes chemical transformations that change its properties and position. It is possible that what we perceive as the presence of nickel is merely a radiation-damaged shell that distorts the true, original chemical composition of the comet, not reflecting its internal nature. Or, more intriguingly, there is a hypothesis that the 3IATLAS formed in a star system where the elemental ratios were completely different from ours. The stellar composition is far from identical across all stars, old, young, those born from gas clouds enriched by various types of supernova explosions. Each star has its own unique recipes of chemical elements, and it is quite possible that this unique composition left its mark in the makeup of the comet formed in its vicinity. Perhaps the origin of the 3IATLAS objects is linked to a region of the galaxy where nickel was significantly more abundant relative to iron than in areas where we usually observe such objects. It is quite likely that the star in which these comets were born had unusual chemical characteristics, and these features are forever imprinted in every molecule of this cosmic fragment. At the same time, it is important to remember that spectroscopy is a very complex science. Detecting weak emission lines against a bright background is an extremely challenging task that requires high precision and delicacy. There are certain detection thresholds below which any traces of iron may remain unnoticed. It is possible that the amount of this metal in the comet was less than the detection limit of current instruments. It is also conceivable that the radiation characteristic of iron is mixed with other spectral features, or that we are simply observing at wavelengths where it does not manifest. Nevertheless, as the comet approaches the Sun and gradually heats up, signs of iron may begin to appear inside. Part 6 of 43. This process would be encouraging, as it would confirm the existence in our universe of mechanisms and processes that allow metals to manifest and become apparent precisely when their presence is most expected. In such a case, we could confidently say that the universe is still full of meanings and patterns, that it is alive and evolving. But what if the situation turns out differently? What if, when the 3-eyed Atlas reaches perihelion, the point closest to the Sun, iron still does not reveal itself, does not begin to emerge from within? And what if the nickel-to-iron ratio in this comet remains completely inverted compared to what we observed previously? That would be a true revolution in our understanding. Such a scenario would mean that planetary systems can produce comets with a chemical composition of metals so different from ours that all existing models and theories would require a complete revision and rethinking. That is why astronomers and researchers are closely monitoring the 3 Atlas comets. Each spectrum, each observation serves as a test of our knowledge and expectations. Every image obtained is an opportunity either to confirm existing theories or to refute them, to open new horizons of understanding. At present, it can be said that the behavior of the 3 Atlas comets more often raises questions than provides definitive answers, and their observations increasingly contradict our expectations. What is particularly interesting is that the third object, a comet that is beginning to activate and show signs of ignition. It is generally believed that as it approaches the Sun, nothing subtle or insignificant occurs. Everything happening was a bright, intense, and simultaneously ominous manifestation, a rich green hue that became so bright and distinct in photographs that it was impossible to confuse or overlook. This vivid green color resulted from two main sources: cyanide molecules and atomic nickel, both capable of emitting intensely in the green spectral range. During the comet's heating process, these sources began to emit more and more strongly, and their intensity increased rapidly, not linearly but at an extremely accelerated rate. That is, the increase in brightness occurred much faster than could be predicted based on simple geometric relationships. This was the peculiarity of the observed effect, its superlinearity, where emission lines intensified faster than any basic physical law could forecast. If we take the distance to the Sun as a basis, then according to the physics laws applicable to inverse square relationships, we would expect that the sunlight falling on the comet's surface would increase fourfold with each step closer. This is the classic inverse square law, fundamental for understanding the propagation of light and energy in space. However, what happened with the emissions of the three main spectral lines known as the atlases was that their intensity increased much faster than expected. This indicated that a completely new mechanism or process was being activated, one that amplified the emission not according to the usual laws, but at a much quicker rate. Astronomers refer to this phenomenon as activation behavior, or the activation effect, implying that at a certain moment, new processes are sharply triggered, like a switch that instantly shifts the comet into a different mode of activity. Imagine a temperature threshold, a specific boundary, upon reaching which, as if by flicking a switch, a radical transition occurs. Below this threshold, the ice inside the comet remains solid, locked, and calm, in a dormant state. But as soon as the comet crosses this critical temperature level, something remarkable happens. The ice begins to subliminate, transforming from a solid into gas, and this process is accompanied by a sharp increase in gas release. New emission lines appear in the spectrum, as if someone turned on a switch, and a new mode is suddenly activated. This effect was so rapid that it seemed instantaneous. One moment the process was off, the next it was fully underway. When activated, it could continue on its own, provided the comet still contained enough volatile substances to fuel this mechanism. It appears that the 3 Atlases had several such switches. First, water was activated, and the activity reached a level at 3.5 astronomical units, already quite anomalous, exceeding all expected values. Then, as the heating continued, cyanide and nickel came into play, brightly green and noticeable in the spectra as the comet kept approaching the Sun. Each outburst, each flare indicated that certain volatile reservoirs, gas or substances stored within the comet, were involved, which began to actively release once a specific threshold was reached. Moreover, these thresholds triggered at different points depending on the chemical composition of the environment surrounding the comet. One of the most plausible models explaining such phenomena involves the presence of extended icy grains within the coma. Instead of considering activity only on the surface of the nucleus, imagine that small icy particles detach from the nucleus and escape with the gas into the surrounding environment. These tiny particles, like miniature icy shards, drift through space, remaining cold and frozen. But as soon as they start to move away from the nucleus and are exposed to constant sunlight, their temperature gradually rises. Eventually, each grain reaches its own temperature threshold, after which it begins to subliminate. As a result, a distributed gas source emerges, emanating not only from the water ice, which possesses a unique characteristic, sublimation at a specific, precisely defined temperature. This means that when a certain temperature threshold is reached, the ice transitions directly from a solid to a gas, bypassing the liquid phase. At the same time, carbon monoxide, or more precisely, methane, which we often colloquially refer to as carbon dioxide, sublimates at much lower temperatures, significantly below those at which water ice sublimates. Carbon dioxide occupies an intermediate position between these two substances in terms of the temperature range in which it transitions into a gaseous state, maintaining its unique properties. If we imagine a three-layer structure, for example, as a complex layered fabric or an onion, we can see that each layer contains a specific type of ice or substance located at different depths or in various regions of this complex sample. In such a case, as this layered structure is gradually heated, the layers are sequentially released and activated. Initially, the substances with high volatility are activated, so-called supervolatile substances capable of easily transitioning into a gaseous state with minimal temperature increase. Then, as heating continues, more common volatile substances with lower sublimation tendencies begin to manifest. Finally, the most resilient and stubborn substances require a significant temperature increase to transition into the gas phase. This process can be likened to gradually peeling layers off a book, each layer disappearing as a certain temperature point is reached. For someone well acquainted with the nature and behavior of comets, such an analogy does not seem unfamiliar. In our solar system, we have observed how some comets behave quite strangely. Sometimes, within a single night, a comet's brightness increases tenfold or more, indicating sudden outbursts of activity. Occasionally, as comets approach the Sun, they begin to split and break into parts because thermal stress destroys their internal structure. There have been cases where comets remained passive until reaching perihelion, the closest point to the Sun, and only then suddenly became active, erupting in bright flashes. However, this object, known as 3IATLAS, exhibits unusual behavior that does not fit conventional expectations. It seems to follow its own, unique activity pattern, unlike any known scenario. This cosmic object is located at very large distances from the Sun, where conditions are so cold and calm that it appears to fall into a state of dormancy, entering some form of internal repose. But despite this, it almost deliberately engages in activity, as if consciously initiating its actions and increasing internal tension. The internal processes occurring within it resemble a complex game, where each step is a preparation for the next, and despite the apparent silence, something important is happening inside. The further this mysterious atlas progresses along its inner path, the more questions arise. Can it still reveal anything else? Will new emission lines or molecules appear, things we did not expect to see? Will its activity be halted at one level, or will it continue to grow, transitioning into new stages? Each week brings fresh data, new discoveries, and often unexpected surprises. This object is not just an ordinary, predictable comet, but a real drama unfolding right before our eyes in real time. Moving on to the next part, one might ask, where did this object even come from? Every object in space contains a unique history recorded in its trajectory. The path it follows and the laws governing it help us understand its past and origin. The trajectory of the three atlases is not just a random description of their movement, but a vast story spanning billions of years and thousands of light years. It can be compared to an ancient chronicle told through the journey these objects undertake. This trajectory is a hyperbola. The answer to this question turned out to be surprisingly unexpected and even a bit astonishing. Let's try to understand what structure our galaxy has and how it is organized internally. It turns out that the distribution of stars in our galaxy is not a matter of chance or chaos, but a complex, well-thought-out system with its own specific organization. Primarily, most stars, including our Sun, are located in the so-called thin disk, a thin, relatively flat, and bright structure that occupies the central place in the galactic system. This disk is a plane where a rich stellar population is concentrated, consisting of young and relatively metal-rich stars orbiting the galaxy's center at a certain speed, following roughly similar paths. However, the galaxy's structure is not limited to just this thin disk. There is another important component, the so-called thick disk. It differs significantly in its origin and characteristics. This is an older population of stars moving along more inclined, sometimes quite eccentric orbits, occasionally extending far beyond the plane of the thin disk. These thick disk stars are elongated vertically, making them visible as something akin to wings, extending upward and downward across the galaxy. Their orbits do not coincide with the flat motion of young stars, and they differ in their chemical composition. Since these stars formed much earlier than most young stars, their age is an important indicator. They formed during an era when there were far fewer heavy elements around, that is, elements that make up rocky and metallic particles necessary for planet formation. As a result, stars of the thick disk have lower metallicity, meaning they contain less iron, magnesium, silicon, and other elements that today play a significant role in the formation of Earth-like and other planetary bodies. These stars are a kind of ancient witnesses to the early epoch of the galaxy, formed at a time when the surrounding gas and dust were not yet enriched with heavy elements. Now, let's consider the hypothesis regarding the origin of the comet called Tria Atlas. Its orbital parameters suggest that it could have belonged to the stellar population of the thick disk. If so, it might have come from an era when our galaxy was still young and less enriched with heavy elements. In that case, this comet could have formed under very ancient conditions, possibly even before our solar system was born. Given that the age of our solar system is approximately 4,600,000,000 years, the Tria Atlas comet could have originated much earlier, at a time when the galaxy was still young and heavy elements were rare. It is plausible that the age of stars in the thick disk often exceeds 7 billion years, which means this comet could have existed in those distant epochs, when Earth still lacked ancient oceans and the first plants. In other words, it could have carried ice and rocks from a time when our galaxy had not yet given birth to the Sun, and when the galaxy itself was in a state of much lower heavy element enrichment. This is of significant chemical importance. The gas cloud from which the thick disk of stars formed long before contained considerably fewer heavy elements than the cloud that gave rise to our solar system. Over time, supernova explosions became more frequent, enriching the interstellar medium with heavy elements and making the galaxy more chemically diverse. As a result, the first generations of stars consisted almost entirely of pure hydrogen and helium, resembling the primordial matter of the universe. Later, with the formation of new stars, heavier elements, metals such as iron, magnesium, silicon, and others, began to be incorporated into their composition. Subsequently, these elements accumulated, enriching the interstellar medium. The second and third generations of stars, including our Sun, now contain several percent of metals. Stars in our galaxy are scattered across tens or even hundreds of thousands of comets, and some of them, possibly entire planets, may have been ejected from their original systems and now drift freely through interstellar space. These celestial bodies, like messages written from a distant distance, may contain hidden signs, 3 atlases, like a single letter in a complex script sent across thousands of light years. And we are only beginning to learn how to decipher them, gradually approaching an understanding of their true meaning. In this part of our story, we discuss what accompanies such comets and what makes them special. After all, comets are not just accumulations of ice and rocks, or lifeless cargo drifting through space. They are carriers of a rich and complex composition, like freight ships transporting molecular reserves of the environment in which they formed. The 3 atlases, like 3 eyes capturing something very unusual, carry something mysterious and very important for understanding their nature and origin. Earlier, we spoke about water, which is carried away into the vastness of space at a speed of about 40 kilograms per second, reaching distances where, according to the generally accepted laws of currents and atmospheric phenomena, it simply should not exist. This water, or rather molecular fragments of hydroxyl remaining after sunlight breaks them apart, was the first sign that there is something unusual in the composition of this comet. But the story does not end there. Water is only the initial stage, the first chapter in the story of what makes this comet special. The real shock is the presence of carbon dioxide. Observations show that on the Tria Atlas, the ratio of carbon dioxide to water in comets here is extraordinarily high. Compared to comets within our solar system, where water predominates, being the main substance that determines their activity and dynamics, carbon dioxide is also present but in smaller amounts, playing a more auxiliary role. In the case of the Tria Atlas, the situation is radically different. According to some measurements, about 95% of the volatile substances in this comet are carbon dioxide, while water makes up only a small part of this volume. This completely changes the usual perception of such bodies and causes surprise, as it contradicts what we are accustomed to see in our home system. Why did this happen? Why is this comet so rich in carbon dioxide? One hypothesis relates to the temperature of the ice layer from which it formed. Ice composed of carbon dioxide condenses at higher temperatures than water ice. Therefore, if the Tria Atlas formed in the region of its protoplanetary disk closer to the parent star, where the temperature was higher, it could have predominantly absorbed carbon dioxide, losing some of its water reserves in the process. Perhaps the radiation field of the parent star was different from that of our Sun and affected the icy components according to different laws. Alternatively, the giant planets in this system, if they existed, could have migrated along different orbits, stirring and mixing the disk, which led to an unexpected redistribution of materials and the formation of unique comet compositions. Additionally, there is another important component, cyanide. Usually, comets contain a cyanide molecule, or CN, which gives many bodies a greenish hue. But in the case of the Tria Atlas, cyanide appeared later, after water, during the so-called warming phase associated with changes in composition and temperature. In our comets, cyanide and water typically appear around the same time because they have similar sublimation temperatures, meaning they transition directly from solid to gas. The delayed appearance of cyanide relative to water influences the gas-to-dust ratio within the comet, which plays a crucial role in determining its internal structure and disintegration mechanisms. These proportions help us understand how fragile or stable this celestial object might be under external forces. At this point, it is worth raising a question often considered the elephant in the room, the panspermia hypothesis. This idea suggests that life, or at least its building blocks, could have spread throughout the universe by traveling on comets and asteroids, acting as cosmic messengers. To support this theory, one should recall the so-called Tria Atlas, a collection of samples containing water, organic compounds, and cyanide. Cyanide is regarded as one of the key precursors in prebiotic chemistry because it plays a vital role in synthesizing more complex organic molecules necessary for the emergence of life. If you were designing a comet to seed a particular planet with a unique chemical composition, you would undoubtedly include these components. However, it is important to remember that all these considerations are merely speculations, hypotheses based on logic and observations but not supported by direct evidence. In particular, there is currently no evidence that these three atlases, or any other comets, actually contain living organisms or were their carriers in the past. It is also unknown whether any comet has ever been capable of transferring living life forms throughout its existence. The panspermia hypothesis appears very attractive and, in theory, quite plausible, as it explains the possible spread of life across the galaxy. But it faces serious challenges and numerous questions for which science has yet to find definitive answers. One of the main difficulties is the harshness of space conditions. Cosmic radiation is a powerful destructive factor capable of breaking down complex molecules that constitute biological substances over millions of years. In the interstellar space, where there is no atmosphere or protection, high-energy particles colliding with molecules can destroy their structures. Similarly, ultraviolet radiation from stars, penetrating the emptiness of space, destroys DNA, proteins, and even simple amino acids, which are considered the building blocks of life. For living organisms or at least their chemical components to survive a long interstellar journey, they must be hidden deep inside a comet. This means they need to be protected beneath a thick layer of ice and rock, shielding them from destructive factors. Such a layer should be at least several meters thick, the thicker, the better, to ensure reliable protection from radiation and ultraviolet radiation. At the same time, these molecules, resulting from synthesis within the parent comet system, could preserve their properties over billions of kilometers of travel. They could have formed in a planet's atmosphere, on its surface, or as a result of chemical reactions inside the comet itself. If these molecules are sufficiently stable and well protected, they could indeed survive a lengthy interstellar voyage and reach their destination, landing on a new planet or in another system. If we had the opportunity to analyze such space samples, we could gain unique insights into the processes and conditions that existed in distant worlds. These molecules could tell us about the chemistry of an alien planet's atmosphere, metabolic pathways that existed in extinct biospheres, or even the chemical composition of long-gone ecosystems. They are, in a way, messages written in carbon, nitrogen, and oxygen, waiting to be deciphered. That is why some scientists dream of intercepting one of these interstellar objects. Not just observing it from Earth, but sending a spacecraft capable of matching its speed, and upon reaching it, landing on it, drilling into its surface, and collecting samples for analysis. The discovery of mysterious radio circles and other unusual structures in space is a task that is far from being solely reliant on automated algorithms or powerful machine learning methods. In fact, in most cases, it is the human eye, supported by intuition and attention to detail, that becomes the main tool in identifying phenomena hidden in the vast expanses of the universe. Sometimes, those behind this observation are not professional astronomers or space research specialists at all. Their role is simply to carefully examine and analyze data, and in some cases, to notice something unusual and truly astonishing. Allow me to tell you about mysterious radio circles and their unusual properties, which many have never even heard of. These structures were only discovered in the 21st century, in 2019, which, by astronomical standards, makes them almost new discoveries that we still have much to learn about. These phenomena can be imagined as vast, ringed regions that are visible exclusively in the radio spectrum. They cannot be observed in optical or infrared light, which makes them particularly mysterious. To see them, one must point a radio telescope at a specific patch of the sky, and suddenly a picture appears before the eyes. Perfectly defined rings, sometimes stretched across hundreds of thousands of light years, resembling enormous cosmic smoke rings drifting through the boundless darkness of space. What are these enigmatic structures? To this day, no one knows their true nature for certain. The most common theory suggests that they may be caused by galactic winds or shock waves emanating from supermassive black holes located at the centers of galaxies. However, honestly, debates and research are still ongoing within the scientific community, as these objects remain a real challenge for scientists. They are extremely rare and difficult to detect because their faint radio emissions blend with background radio signals, making them virtually invisible to most automatic detection systems. Typically, automated algorithms, powerful systems designed for rapid analysis of vast datasets, discard such objects because they are tuned to find point sources or small clusters, while large, diffuse rings often go unnoticed. That is why human participation, attention, intuition, and the ability to notice something unusual becomes especially valuable in this field. In citizen science projects, such as the R at Home project, volunteers undertake the task of examining radio continuum maps without using automatic filters or algorithms. They simply compare images, look for anomalies, and pay attention to those parts of the sky that seem unusual to them. They are not searching for any specific objects. Their task is broader and simpler: to notice something strange that doesn't fit the usual pattern. And it was precisely through this approach that, in March 2025, one volunteer observed something extraordinary, which turned out to be a real discovery. The object, designated ROJ 13134, was recorded as ROJ 13134 6.9 plus 500,320. It's a striking name that sounds like a code from some scientific file, but what is far more important is what it represents: a pair of intersecting radio rings forming a figure-8 shape. These two rings overlap in the sky, creating a complex and very bright pattern. Today, this is the most distant and most powerful of the known radio rings discovered through research. And surprisingly, it was not found by automated systems or professional astronomers, but by a person who decided to spend a little time examining radio images. All of this became possible thanks to the use of low-frequency range maps, known as LF, as well as the operation of a network of radio telescopes scattered across Europe. These devices collect vast amounts of data that would be difficult to analyze manually in full. Therefore, most of the information is processed by automated pipelines that filter out potential candidate objects based on specific criteria. Recently, one of the volunteers in a citizen science project discovered a grand radio galaxy with a unique ringed structure surrounding it. This discovery was particularly surprising because, at the boundary of this cosmic mass, he noticed an unusual ring at the end of a jet, a phenomenon not predicted by existing theoretical models and understanding. Such findings are essentially objects that could be irretrievably lost in the endless stream of data if the observers monitoring the universe did not pay attention to them. They serve as a reminder that in the era of mass data collection, each such unusual detail could become a key to new discoveries if we learn to notice them amid the multitude of routine data. This case carries an important lesson that extends far beyond radio astronomy and space research. We are on the verge of an era when the volume of incoming information becomes so enormous that traditional analysis methods are no longer capable of ensuring the timely detection of all significant anomalies. For example, after the launch of a new observatory named after Vera Rubin, which is expected to be operational soon, it is anticipated to generate about 15 terabytes of data each night. Over time, this amounts to roughly the amount of information contained in 15,000 tablets, or, in other words, an entire dataset that, over 10 years of operation, will accumulate so much data that no human team can fully process or analyze it manually. No existing algorithm can identify all possible anomalies, unusual cases, or strange phenomena within this flow. Therefore, it is necessary to use both automated processing systems and human judgment. We need machines capable of performing large-scale analysis and detecting potential deviations, as well as people who can pay attention to cases that go beyond standard scenarios and patterns. Now, imagine combining this approach with the concept of the 3 atlases, large systems that collect and structure data about the cosmos. In this context, a question arises: could an amateur scientist have noticed early signs of unusual phenomena? Could someone studying spectral data have previously detected the presence of nickel without iron? Could an observer monitoring comet activity have wondered, why is this comet active so far from the Sun? Perhaps yes, and perhaps no. The main point is that such anomalies, like those recorded within the framework of the 3 atlases concept, benefit from having as many eyes as possible observing the data. Professional astronomers have extensive experience, solid training, operate within a well-understood context and knowledge base, and often work under time constraints. However, they also have certain expectations, models they aim to confirm, and time pressure that can sometimes prevent them from noticing everything unusual. On the other hand, amateur and citizen scientists approach space research from a completely different perspective. They are not bound by strict models, are not limited by expected scenarios, and therefore can freely observe what is happening, often noticing things that escape the professional eye. It is precisely such enthusiasts, dedicating part of their time to observing stars and celestial objects, who have long demonstrated notable successes. There are stories of amateur astronomers being the first to discover supernovae, find new asteroids, and monitor variable stars. For example, a Japanese amateur astronomer named Kawai discovered several comets during supernova observations, and a British amateur named Andrew Gray was among the first to record an unusual brightness flare in a star. These cases are not coincidences but clear evidence that passionate individuals equipped with telescopes or access to data can make important discoveries simply by carefully observing the universe. The future, apparently, belongs to such collaboration, When telescopes soon begin to automatically process and systematize vast amounts of data, amateur and citizen scientists, people passionate about the idea of extraterrestrial civilizations and simultaneously prone to seeing aliens in every data anomaly, along with professional astronomers, for whom such situations pose a serious challenge, understandably express concern. Major scientific organizations, such as the Royal Astronomical Society and other respected professional groups, actively discuss and analyze this issue, striving to find a balance between public engagement in science and maintaining high standards of scientific rigor. On one hand, involving the general public in data processing helps significantly reduce research backlog. It allows projects to analyze much more information than if only professionals were involved. This approach not only accelerates the discovery of new phenomena but also generates lively public interest, inspiring genuine enthusiasm and a desire to participate in scientific discoveries. It is a form of citizen engagement in scientific activity that not only broadens research possibilities but also promotes science popularization among society. However, at the same time, quality control of the obtained data is extremely important. In science, even the most exciting discovery is considered credible only if it has undergone rigorous verification, cross-analysis, and peer review by experts with relevant knowledge. Such a process requires a certain amount of time and professional training. False alarms are a real and quite common problem, often occurring when someone spots an unusual object or event, thinking it might be evidence of extraterrestrial technology or other mysterious phenomena. In most cases, astronomers have to spend days or even weeks conducting careful observations to determine whether the detection is related to a genuine astronomical object or merely noise from instruments, a trace of a passing satellite, or the influence of cosmic rays. All of this involves time costs that could be directed toward discovering truly important phenomena if not for the necessity of thoroughly verifying each report. As the number of false alarms increases, professional astronomers naturally become skeptical of amateur reports. Their confidence in new discoveries diminishes as the number of suspicious signals grows, and the ratio between real signals and noise worsens. As a result, fatigue accumulates, and confirmation bias develops, a psychological effect where a person tends to notice only what confirms their initial expectations, ignoring everything else. If seekers of new mysterious phenomena focus on a specific object or effect, they often find it, even if it exists only in their imagination or as a coincidence. This phenomenon is widespread even among professional astronomers. However, they have trained methods for evaluating and verifying data, which significantly reduces the likelihood of errors. For amateurs, such verification methods are often inaccessible or require specialized knowledge that many do not possess. As a result, they may see patterns where none exist or interpret random data fluctuations as evidence of unusual phenomena, convincing themselves of their truth. This leads to high-profile claims about giant megastructures around Tabby's star or reports of strange signals in pulsar data, which are actually just random outliers or artifacts. An additional problem is calibration of equipment and the related measurement errors. Professional astronomers know well how to properly assess and account for these errors, understanding when a signal is truly statistically significant and warrants attention, and when it is just noise or random fluctuations. Fans may lack such knowledge or experience, and their reports are often based on deviations of just 1 sigma, which, within the overall statistical context, is a negligible variation that does not warrant serious attention. On the scale of all astronomical science, such small deviations do not confirm the presence of any unusual phenomena. Additionally, there is a limitation in processing capacity, the ability of professional researchers to handle and analyze the vast amount of incoming data. When a citizen science project implements a multi-tiered verification system, where several independent volunteers must observe the same object or record a specific event before it reaches the attention of professional scientists, it becomes a powerful tool for filtering out false signals and errors. This scheme provides much higher detection accuracy by eliminating the influence of random mistakes or subjective failures of a single individual. The possibilities embedded in such a methodology are vast and diverse. Using crowdsourcing approaches to identify anomalies allows for more thorough and large-scale analysis of enormous data sets, which is often impossible for a single specialist or small team. When multiple independent observers simultaneously note the same event, the likelihood of missing or misinterpreting it is significantly reduced. If one person, for some reason, fails to notice or makes an error, others with different experience and perspectives can pick up the signal, identify a pattern or anomaly that might have escaped the attention of one individual. This cross-checking helps to identify true anomalies, reducing the risk that a critically important event will go unnoticed or be misinterpreted. Let's consider an example from astronomy. Returning to the Third Atlas, an extensive database and collection of observations. Could an amateur astronomer, not a professional scientist, detect an early anomaly, such as the appearance of an unusual radioactive nickel line? Spectral data used for such observations are now accessible to anyone interested. They are published openly, and anyone with suitable software and skills can download and analyze this data. However, spectroscopy is a highly complex art that requires deep understanding, as it involves correctly identifying spectral lines, calibrating wavelengths, and assessing the signal-to-noise ratio. All of this demands precision, patience, and knowledge. Careless or superficial handling of spectroscopic data easily leads to errors or misinterpretations. With proper training, guidelines, and collaboration within a community of like-minded individuals, someone is quite capable of noticing unusual signs or anomalies earlier than they make headlines and cause a stir. Similarly, monitoring the rate of water or other natural resource extraction can be approached in the same way. For example, graphs of comet brightness and measurements of their luminosity over time are often provided by amateur astronomers. If these enthusiasts studied ultraviolet data obtained by the Swift telescope and were trained to recognize unusual activity patterns, they could detect superlinear increases in brightness within the Atlas Tria. They might then say, "This doesn't resemble the behavior of an ordinary comet," before professional research confirms it. History has repeatedly shown that citizen scientists can make discoveries often overlooked by professional experts. This approach is effective and supported by many practical examples. For instance, the transit method of discovering exoplanets, monitoring tiny dips in a star's brightness when a planet passes in front of it, has been significantly improved thanks to efforts by amateur astronomers analyzing data from the Kepler Space Telescope. Initiatives like the Planet Hunters project have helped discover several confirmed exoplanetary systems. Similarly, amateur asteroid hunters have found numerous near-Earth objects that, for various reasons, professional studies either missed or ignored. Additionally, people searching for new stellar flares regularly outpace professional astronomers in discovering bright new events because they observe the sky every night with small telescopes, while professional telescopes are often booked months in advance. This important fact demonstrates that citizen scientists serve not as competitors but as a complement to the capabilities of professional institutions. It is crucial to emphasize that the topic is not about Mercury, the planet closest to the Sun, which has recently become particularly prominent in the evening sky. It has moved into a position where it can be observed after sunset, shining brightly high above the horizon. This phenomenon delights astronomy enthusiasts and those who simply enjoy gazing at celestial bodies, as Mercury can now be seen almost every evening, with its bright silhouette easily distinguishable against the darkening sky. At the same time, another significant event is taking place deep in space. The largest object in the asteroid belt, Sirius, has reached opposition with Earth. That is, it is positioned directly opposite the Sun in the sky, which means it is at its maximum brightness and closest to Earth. During such a configuration, the star and the asteroid are on opposite sides of the celestial sphere, making them especially visible and bright to observers. When people started observing the night sky, various messages and hypotheses began to appear on social media. Some noted that they could now see Mercury, others mentioned a series of events, and some paid attention to the mysterious interstellar comet called Tria Atlas. This comet seemed to behave unusually, almost as if it possessed a living being, as if it were actively participating in this cosmic spectacle. Some wondered, could these phenomena be related? Is there some cosmic alignment of forces happening in the sky? Does the activity of the comet influence the gravitational fields within the solar system, as if they are somehow provoked or amplified by its presence? These questions often arise in the minds of observers seeking patterns and connections. However, it is important to clarify, there are no links between these events. In response to possible guesses and hypotheses, it can be confidently said that there is no influence or correlation between Mercury's orbit and the gas concentration in the interstellar comet. The position of the Oort cloud, sometimes called the cometary cloud, relative to Earth has no impact on the chemical processes occurring billions of kilometers away, where the comet is located. These are two independent situations that coincidentally occurred at the same time and now seem connected only because we tend to seek patterns. Humans are inherently creatures who create a system of pattern recognition within themselves. We are programmed to try to find explanations for everything happening, as it is essential for our survival. Our ancestors, noticing that some berries caused poisoning and that animal tracks indicated the presence of food, had a much higher chance of survival than those who did not observe such patterns. Therefore, developing the ability to notice and recognize patterns became a crucial aspect of the evolution of the human mind. Our brain is an amazing organ, highly sensitive to detecting patterns. Sometimes this sensitivity becomes excessive, and we start seeing connections where none exist. This tendency is nothing but a manifestation of pareidolia, the phenomenon where a person perceives or hears something where there is actually nothing. In everyday life, we encounter this constantly. Seeing faces in clouds, hearing voices in noise or radio interference, interpreting random sounds as important signals. The same happens with celestial phenomena. The pattern recognition system sometimes fails, and we begin to assign unexplained significance to what we observe. Ancient cultures were well aware of the power of such perceptions. They observed the positions of planets and drew important conclusions for their lives based on these observations. When a comet appeared during a battle or significant events in the sky, it was believed that the gods were angry or trying to warn people. When planets gathered in one part of the sky, it signified the birth or death of an important person, ruler, or chieftain. These interpretations were based on beliefs and observations passed down from generation to generation. An example of this is the story related to a century ago, in the year 1000. Perhaps the awakening of the comet occurs due to some internal resonance caused by the peculiarities of the solar system, or from the influence of external forces such as gravitational disturbances. It may be reacting to changes in its trajectory, which are subject to minor, seemingly insignificant shifts caused by various factors. It is quite plausible to assume that all these phenomena are merely part of a broader pattern that has yet to be understood. Astronomers have long calculated and analyzed many aspects, and it has been found that the gravitational influence of the largest planets on objects in the distant parts of the solar system is practically imperceptible. For example, Mercury, the closest planet to the Sun, is slightly larger than our Moon, and its mass is just a small fraction of the entire solar system. It is very far away, and its gravitational impact on objects beyond its orbit is minimal. Similarly, smaller bodies such as asteroids or small moons exert an even lesser effect. As a result, the combined gravitational forces from all the planets could not, in principle, significantly influence the behavior or trajectory of the comet we observe hundreds of millions of kilometers away from these planets. Specifically, the behavior of the comet that currently draws our attention is determined by internal processes occurring within it, the influence of solar radiation, as well as its material composition and structure. All these factors have a much greater impact on its movement than the position of any planet, whether Mercury or someone else. However, despite this, the human mind tends to seek explanations and connections even where none exist, because we crave understanding, and we want events to be interconnected. We prefer to see some pattern because random, isolated phenomena seem meaningless, chaotic, and evoke a sense of uncertainty within us. When we begin to perceive the activity of the comet as related to the positions of the planets, even if this connection is unconfirmed, we ascribe meaning and order to it. Otherwise, there is a risk of perceiving the universe as a place where strange things happen randomly and independently, which can cause psychological discomfort, a sense of unpredictability, and even anxiety. Our desire to find confirmation of these connections intensifies as we actively search for them. And once a person starts paying attention to possible links, they will find them almost everywhere, in various phenomena, facts, and events. Let us remember that Mercury, with its short orbit and frequent oppositions, was a prominent object in the sky even during previous comet observations. When scientists discovered another unusual object, yet another bright comet, it happened at a time when Mercury was especially visible in the sky, positioned at opposition. However, it is important to understand that the fact that Mercury is visible several times a year and that it regularly reaches oppositions has nothing to do with what was happening with the comet. Equally important is that unusual astronomical discoveries and the detection of new celestial bodies occur constantly, regardless of the positions of the planets. But our brains tend to filter the flow of information and remember only those moments that align with our beliefs and expectations. Modern social networks amplify this confirmation effect many times over. In the past, if you had an idea that the arrangement of planets influences comet behavior, you could share it with friends and family, and most likely hear a skeptical, "That's nonsense," in response, after which your hypothesis would fade away. Today, thanks to the internet, your opinion can instantly gain popularity and gather a community of like-minded individuals. You share links, images, diagrams showing supposed planetary alignments, and someone adds new evidence. Others spread this further, and eventually a full-fledged alternative theory emerges, competing with scientific explanations. Perhaps this is not a natural phenomenon at all, the mysterious comet that recently drew the attention of observers and scientists. Maybe it is not a cosmic object formed through natural processes at the edge of the solar system, but something else, created by human hands or technological means that cannot be immediately explained. It is quite possible that this object responds to signals or radiation emanating from planets or space stations, and perhaps it is part of a larger, grander mechanism about which we know almost nothing. Maybe this mechanism is part of a complex system long integrated into outer space and hidden from our view, operating under simple laws that we cannot even begin to imagine. All this suggests the existence in our universe of something much more mysterious and complex than it appears at first glance. It opens the door to yet another, more strange and tangled chapter of this story, the realm where mechanisms of mystification, unfounded conspiracy theories, and human tendencies to turn scientific mysteries into cultural myths collide. People are often inclined to attribute supernatural or occult significance to unusual phenomena and inexplicable events, creating legends and speculations around them that often have nothing to do with reality. This part of the story is the 9th installment, and it is filled with uncertainty, ambiguity, and questions that currently have no answers. An update to these reflections comes from October 2025, which raises even more questions. Was all of this even real? Or are we dealing with an illusion, an effect created to distract attention, or a clever piece of information cover-up? From time to time, such questions arise in the minds of observers, especially when it comes to mysterious phenomena or events that remain unexplained. For example, on October 8, 2025, Blue Origin conducted a mission codenamed NS-36. 6 passengers participated, and the flight itself lasted only about 11 minutes. Among the participants was one mysterious individual, a pilot whose name remained strictly classified until landing. Initially, the entire operation appeared to be a standard launch, a routine space tourism mission no different from previous ones. The capsule launched, crossed the Kármán line, entered microgravity conditions, performed a few minutes of free flight, and then, using parachutes, gently landed in the deserts of Texas. Everything went flawlessly, as scheduled, confirming the company's reputation as one of the leading private space travel providers. It was yet another successful launch, the 15th mission within the space tourism program developed and operated by the company. A routine event that has become familiar and commonplace, almost an everyday occurrence in the modern world. At least, that is how this situation was portrayed in official reports. Television channels like BC News reported it, and Medium published an article detailing the mission's progress. Several space journalism specialists even shared their comments on social media, particularly on Twitter. But what is truly astonishing is that after one of the passengers landed, his identity, existence, and role suddenly went beyond the usual boundaries of transparency. This crew member was discovered at a moment when the crew was already returning to Earth. And here begins the strangest part. The individual, who wished to remain anonymous regarding the mission itself, later agreed to reveal his name, and this surprised many. Of course, there is probably nothing unusual about wanting to maintain confidentiality. People constantly pay for the right to remain unknown, especially when it involves private individuals participating in space travel. But there is one very important detail that raises questions among attentive observers. Was this mysterious passenger, appearing in the footage, a real person, or was his image merely part of a carefully woven plot designed to explain the absence of pre-flight advertising, which usually accompanies such events? Did the capsule really launch on October 8, as officially stated, or were all the footage capturing that flight recorded earlier and then repackaged with a new date to create the illusion of a recent, current event? Such thoughts are essentially a manifestation of paranoid thinking, a tendency toward conspiracy theories, where a person begins to perceive everything around them through a lens of distrust, sees shadows where there are none, and unwarrantedly doubts any information. However, sometimes the absence of direct evidence seems particularly convincing. When something should produce sounds or leave obvious traces, but does not, a reasonable question arises. Why is that? Shouldn't we consider the possibility that something is being concealed or that it was done differently than expected? Let's try to imagine a situation, for example, April 2025. That was only half a year ago, and during that period, Blue Origin conducted another launch of a space capsule from a series of missions called New Shepard, which unexpectedly gained widespread public attention. Unlike previous launches, this one caused not only interest but real excitement, triggered not by technical failures or errors, but by the fact who was on board the spacecraft. Among the passengers were well-known figures such as singer Katy Perry, popular TV host Gayle King, and the first all-female crew, which in itself was a unique event in the history of spaceflight. These celebrities, with millions of followers on social media, people whose popularity and influence extended beyond ordinary measures, all made such a launch a headline-making event and a topic of discussion on the internet. And that is exactly what happened. However, what occurred was not quite what Blue Origin itself expected. A few hours after the live broadcast ended, when millions of people were watching, social media exploded with a wave of conspiracy theories. People began speculating that the footage of the flight was fake, that everything was shot in a studio, and that there was no real space journey. They carefully analyzed every frame of the footage, and every discrepancy became a reason for new guesses. For example, attention was drawn to the crew's hair in the microgravity conditions. Participants in the discussion questioned whether the hair was behaving correctly. Did it look like a wig or computer-generated images? Or perhaps it was real hair, but reacting to air currents and static electricity in such a way that it created the impression of unusual movement. Details about the capsule's hatch also did not go unnoticed. Someone claimed that its opening mechanism differed from previous launches. Comparative photos were posted on social media, showing that the latch could have been positioned on the other side or that the door opened outward rather than inward, as previously believed. All of this was presented as evidence that something had been done differently than before. Then followed even stranger and more exaggerated assumptions. Claims appeared online that the screens displayed green colors and that passengers were filmed using studio sets, specifically prepared scenes with fake windows showing pre-recorded footage of Earth. Allegations against the flight's creators sounded even more fantastic. It was claimed that the passengers' hands looked like mannequin hands, too smooth, as if cast from plastic, creating an impression of artificiality. Complaints arose about the absence of visible scorch marks or damage on the capsule's surface after entering the atmosphere, which, according to conspiracy theorists, meant that the capsule never existed at all. Every tiny detail, every insignificant feature, in our modern era, as space exploration continues to develop with relentless intensity, we face astonishing phenomena that challenge our conventional understanding of the universe. Recently, we observed two events related to the same rocket, conducted just 6 months apart. Both missions used the same basic design and profile, yet the reactions to them were completely different. One sparked a real storm of attention, generating numerous discussions, doubts, and hypotheses, while the other went almost unnoticed, hardly eliciting any responses or interest. The question arises: what is more suspicious, the fact that one drew so much attention while the other remained unnoticed, or perhaps, conversely, that the second seems more mysterious due to its unremarkable silence? This dilemma highlights how complex and multifaceted our reactions to cosmic phenomena can be. So, we move on to the 10th part of our series, titled Cosmic Secrets as Mirrors. In it, we continue to observe how the universe constantly throws unexpected and sometimes even astonishing surprises at us: mysterious objects, signals without clear meaning, and phenomena that seem to violate all our established models and perceptions. Each time we encounter them, we inevitably do two things. First, we try to understand them from the perspective of modern science, seeking explanations and constructing logical chains. Second, we project our own fears, hopes, and fantasies onto these mysteries. This process appears to be an integral part of our perception of the cosmos, for every new discovery is simultaneously a challenge and a mirror of our inner world. Let's recall a story that took place in the distant year 2000 and something, the case of Oumuamua, the first confirmed interstellar object to pass through our Sun. It appeared as an elongated, slightly reddish, tumbling mass, whose speed gradually increased as it left the bounds of our solar system. This object was noticeable due to its unusual shape and movement, and its acceleration, slightly more significant than what was predicted based solely on gravitational calculations, prompted scientists to ponder. At that time, various explanations emerged. Some suggested that it might have been emitting a small amount of volatile substances, creating a thrust similar to that observed in weak comets. Others spoke of a hydrogen iceberg, frozen H2 sublimating invisibly to the eye, or a fragment of a destroyed planet, whose shape and rotation produced an effect of radiation pressure. But among scientists, there were also those who proposed more unusual hypotheses, including the possibility of artificial origin. What if Oumuamua was not a natural body, but, say, a light sail or solar sail, a thin sheet of material propelled by starlight? In that case, its acceleration could be explained by the force of light rather than just gravity. Such a scenario could imply that it was a probe from another civilization, designed to explore the surrounding space, or a discarded piece of space debris left behind by a long-extinct alien culture. These ideas may sound fantastic, but it is precisely from such hypotheses that new directions of search and reflection emerge. The same story repeated itself with the star known as Tabby's star, or KIC 8,462,852. It attracted the attention of astronomers due to peculiar patterns in its light behavior. In the view of the Kepler satellite, this star exhibited deep and irregular drops in brightness, sometimes reaching 20% or more. As far as we can judge, no planet is capable of causing such significant darkening, since no planet is large enough or dense enough to completely block such a large flux of light. Moreover, these brightness dips occurred irregularly, without recurring cycles. In the world around us, we sometimes see faces where none exist, shapes drift in clouds like animated shadows, and amid the noise of white radio traffic, we catch whispers of voices speaking behind the limits of perception. At the same time, among endless astronomical anomalies, we seem to see reflections of the mind manifesting in strange cosmic phenomena. This is not foolish fantasy or mere imagination, but the natural functioning of our brain. For we are pattern recognition systems, systems designed to find the familiar among the unknown, and therefore prone to errors, false alarms. It is better for our perception to mistakenly interpret a shadow as a predator than to miss a real threat. Such is the nature of our psyche. However, there is another, deeper reason for our feelings and aspirations: existential longing, a craving for contact. It is so important for us to feel that we are not alone in the universe. Deep down, we want to know that beyond the boundaries of our star systems, there are other sparks of consciousness, other intelligent beings just as curious and seeking answers as we are. Every anomaly, every unusual flash or strange phenomenon in space is an opportunity, a door that can be opened to look beyond the familiar and discover something extraordinary. That is why we persistently explore these mysterious moments, doing everything possible to expand our knowledge and understand the nature of all existence. The three images are like a mirror reflecting our inner world. In their bright green glowing shell, we see not only cosmic objects but also our own curiosity, our passion for seeking meaning, and hope that the universe is more astonishing and strange than it appears at first glance. Perhaps this belief will be justified, and someday we will encounter something that completely overturns our understanding, something so inexplicable that it will force us to rewrite the laws of physics or admit that we are not alone. But until that day comes, we continue to observe, explore, and search. Currently, we have one comet, and although it seems strange and exciting, perhaps the most unusual of all, it is most likely just another celestial body. And that is quite enough, because even the mysteries of nature, even the most enigmatic and unusual ones, are part of that wondrous reality we strive to understand. A mystery in itself is already an important part of this world because it reveals new horizons, new facets of knowledge. In this book, called The Archive of Alien Systems, there is a special concept. Imagine a galaxy as a vast library. However, in this library, instead of books, there are objects and artifacts left by the stars and planets themselves. These are comets, asteroids wandering through interstellar space, planets that drifted away from their systems, and even entire planets ejected from their systems, roaming freely without connection to any particular star system. Each of these objects is like a message in a bottle, a kind of communication from the depths of space containing information about the star system from which it was cast out. Sometimes, almost by chance, one of these bottles reaches our shores, falling into the hands of scientists and explorers. This is how the concept of interstellar objects arises, essentially, postcards sent from distant systems, from strange and mysterious corners of the universe. But it is important to understand that strangers, in this context, do not necessarily imply extraterrestrial intelligence, as is sometimes assumed. Strangers are those who formed under conditions significantly different from those prevailing in our solar system. This is a significant difference, as their origins are linked to different stars, disks with varying compositions, temperatures, and dynamic environments. Each such object is a data point, a separate sample, a drop of information about the conditions in which it formed. By collecting enough of these samples and analyzing them, we find that the behavior of the comet we observe is quite typical for similar cosmic objects. However, the ratio of gas to dust characteristic of it indicates that its formation occurred in a colder environment than that of most other comets known from our solar system. This combination of elements and substances suggests conditions different from the usual, creating the impression that we are encountering something familiar yet somewhat unusual. It's as if this is a dialect of the language of space that we have yet to fully understand. Examining the composition of this comet reveals a whole palette of chemical examples. 3 different types of ice containing water and carbon dioxide flowing at great distances from the nucleus, as well as nickel not bound to iron, and cyanide appearing only during the later stages of its activity. All of this together forms a picture that defies the usual framework of our experience. Its behavior shows no resemblance to what we are accustomed to seeing in comets from our system. It's as if it speaks in a language we are just beginning to decipher, a language in which 3 objects, with 3 completely different chemical compositions, coexist and interact. If we assume that these 3 comets or objects are only part of a much broader population of celestial bodies, then the diversity of their chemical compositions becomes truly staggering. In our galaxy, it seems, there exists a vast array of different types of comets with unique sets of substances. Not all planetary systems produce comets similar to ours. In fact, it can be assumed that most such systems do not generate comets with comparable compositions at all. And one must wonder, what does this mean for our understanding of the universe? In some star systems, comets may have surfaces covered predominantly with nitrogen ice, similar to what is observed on Pluto's surface. In others, methane might be the main volatile component. In systems where stars are much more massive, the snowline, the boundary where water ice can condense and solidify, is located farther from the central star. This means that comets forming under such conditions can carry colder and more heterogeneous mixtures of substances. In systems with migrating giant planets, the situation becomes even more complex. Disks where these bodies form are mixed, moving materials across different temperature zones and creating comets with strange, hybrid compositions that we can only guess at. What if some comets hide molecules that have never been encountered on Earth before? Molecules that are thermodynamically possible but require formation pathways that did not exist in our solar system? Perhaps there is exotic organic matter, unusual ices, and compounds that would excite and surprise chemists. It can be assumed that the universe is a vast, highly diverse world, where the parameter space, massive stars, disk compositions, radiation fields, and dynamic environments, is extremely large. Nature carefully explores this space, and some of its results are sure to seem strange and unexpected to our current understanding. Let's take another important step in our reflections. If we consider that the emergence of life requires certain chemical components, water, organic molecules, phosphorus, nitrogen, and sulfur, then comets lacking these ingredients are essentially sterile bodies. They cannot become sources of life or spread prebiotic molecules to planets. Perhaps most interstellar comets are precisely such bodies, deprived of the substances necessary for life's origin. In that case, one can imagine a comet like Oumuamua as a lifeless stone falling into the silent emptiness of space. However, if even a portion of comets contains the right chemical composition, this part gains special significance. After all, comets are galactic wanderers, travelers between stars. They cross light years of space, and if organic molecules, amino acids, or even more complex compounds are hidden inside them, they could serve as carriers of life's building blocks. Probably, everything around us in this universe is not just a manifestation of life but rather a collection of chemical substances and elements that, under certain conditions, could become the foundation for the emergence of life. If these substances were to land on a suitable planetary surface, they could initiate processes leading to living organisms. Every time we discover a new interstellar object, our sample size increases, giving us a better chance to understand what chemical components and physical processes are present in our galaxy. Currently, we have 3 such objects, and if we imagine that over the next decades their number will grow to dozens, and after 50 years, to hundreds, we will have a unique opportunity to systematically study their composition, trajectories, activity patterns, and changes over time. All of this will enable us to create a statistical picture of what is happening in the interstellar medium and which processes dominate. Perhaps we will find that water-rich comets are common, and that most planetary systems in our galaxy actively produce and eject such bodies. Alternatively, we might conclude that our solar system is a rare case, and that comets rich in water are not so common here, while most other systems form dry, carbon-containing bodies devoid of water. Both of these hypotheses would be extremely important for understanding the general nature of planetary systems and the conditions under which life arises. Perhaps we will even discover a comet containing clear biomarkers, molecules that would be difficult to explain without knowledge of biological processes. These could be, for example, special phospholipids, components of cell membranes, or complex organic substances with a coral-like, carbon-rich composition, as well as isotopic ratios that bear unmistakable signs of metabolic activity. The detection of such indicators would be truly revolutionary, as it would mean that life originated elsewhere in the universe and that its biochemical foundations are not unique to Earth. To date, we have not found a single such sample that would confirm the existence of life beyond our planet. As far as we know, the Tria Atlas is an interstellar object that does not carry life, but it holds important information about its composition and origin. And information is, without exaggeration, one of the main currencies of scientific progress. Every interstellar visitor that accidentally or for other reasons comes into our view is a kind of gift, a sample delivered to our doorstep, and all we can do is examine it more closely to understand its nature and history. This is our main way to expand our knowledge of the universe and how new worlds are born and develop there. Let's move on to a narrower but very important topic, nickel. Returning to this anomaly that has sparked our considerable interest, It's worth emphasizing that we are not just talking about a random peculiarity, but about a valuable clue, a sort of chemical fingerprint of this interstellar object. Such fingerprints allow us to determine its origin and trajectory. Just as fingerprints on a hand reveal who was at a certain place, chemical fingerprints help us understand where this cosmic visitor came from. Stars are, in a way, factories for producing elements. In their cores, nuclear fusion occurs, resulting in the formation of heavier elements from simple substances, hydrogen and helium, such as carbon, nitrogen, oxygen, silicon, sulfur, and iron. When massive stars reach the end of their life cycle, they explode as supernovae, and as a result of this powerful explosion, even heavier elements are ejected into space, with nickel playing a special role among them. These elements, once expelled into interstellar space, disperse throughout the galaxy and over time mix with gas clouds, from which new stars and planets then form. However, not all stars prepare for this. Currently, there is a new hypothesis suggesting that the object known as the Atlas trio may have originated from a very massive and ancient stellar disk formed in the early epochs of our galaxy's development. In this context, it is worth noting that stars belonging to the so-called thick disk are characterized by a lower overall metallicity compared to young stars of other galactic components. However, the ratio of various heavy elements within them can vary significantly. In other words, the composition of these stars is a complex mixture of elements, and the proportions of heavy elements such as nickel, iron, cobalt, and others can differ widely. Considering the nickel enrichment observed in the spectra of the 3IATLAS comets, it is quite reasonable to assume that this reflects the composition of their parent stars. That is, the stars from which these comets formed. In this case, these comets act as tracers, providing evidence of the galaxy's chemical evolution. They offer a unique opportunity to learn about processes that would otherwise be impossible to observe, because through them we can obtain valuable information about the composition and formation history of stellar systems that have long disappeared or are vanishing from the observable universe. Today, we have the ability to analyze stellar atmospheres spectra. This is a primary and quite accurate tool for determining their chemical composition. Spectroscopy allows us to measure the concentrations of elements such as iron, nickel, cobalt, and other heavy metals present in their atmospheres. However, this method has its limitations. Stars located at vast distances are very far from us, and despite technological advances, we can only study a small part of their atmospheres in detail, and only those stars that are currently shining. Moreover, we cannot observe stars that existed billions of years ago and have long since disappeared, leaving behind only their remnants, stellar debris and interstellar gas clouds. In this regard, comets originating from such systems serve as true time capsules. They preserve the chemical conditions characteristic of their formation epoch, often billions of years ago. Thanks to these ancient samples, we can look into the past as if opening a book written on atomic pages. If we had the opportunity to collect samples from the 3IATLAS comets and conduct a thorough analysis of their isotopic composition, trace elements, and mineralogical structure, we could obtain a unique and highly valuable material that is part of an ancient stellar system. Such a sample would allow us to determine its age, possibly billions of years, and understand the conditions under which these objects formed and what their initial materials consisted of. As a result, we would not just obtain a small piece of space, but a genuine fragment of stellar history frozen in atoms, a kind of book written in the language of elements and isotopes. Such an analysis would represent a real breakthrough for science, as it would open a window into the distant past accessible only through cosmic artifacts. Now, let us turn to a rather speculative but intriguing idea that is discussed in certain scientific circles as a hypothesis bordering on science fiction. Is it possible to suppose that anomalous metal ratios in cosmic objects, such as an elevated nickel content, could be signs of artificial origin or processing of these materials? We are not talking about natural processes like thermal metamorphism or other natural transformations, but about traces of technological intervention, materials that have undergone some form of processing or refinement within a highly advanced civilization. Imagine that an advanced spacefaring civilization, engaged in mining asteroids and comets, could produce waste, slag, or tails containing unusual chemical element ratios during its activities. These wastes, in turn, might end up incorporated into comets and asteroids formed from cosmic dust and stones, where remnants of technology could be preserved. But what truly provokes deep reflection and, frankly, some concern, is that each interstellar object, be it a small comet or another space visitor, possesses a unique chemical signature, akin to an individual barcode inscribed in its composition. This signature is a set of elements and isotopes that collectively reflect the characteristic features of the origin and history of that celestial body. Imagine, if we could create an extensive library of such chemical signatures, systematically cataloging the compositions of dozens or even hundreds of interstellar objects, we would gain a unique opportunity to begin mapping our entire galaxy. This map would not merely show the locations of objects but would allow us to correlate their chemical signatures with their trajectories, thereby creating a kind of galactic chronicle. For example, a comet arriving from the direction of the galactic center might have a completely different chemical makeup than one coming from the outer halo, an area beyond the main disk of our galaxy. Similarly, a comet originating from an older, thicker disk could carry traces related to the age of that region, a kind of timestamp embedded in its chemical composition. As a result, we would have the ability to use these interstellar comets as a sort of trail, enabling us to trace the structure and evolutionary stages of our galaxy. Part 33 of 43. Imagine a future where interstellar objects become so widespread and our detection technologies so advanced that we can catalog dozens of them every year. Each month or even each week, we will receive new data, subjecting these objects to spectroscopic analysis to determine their chemical composition and flight trajectories. The trajectories of these objects will be traced back as far into the past as our technology and scientific understanding allow. All this data, their composition, trajectories, speeds, will be stored in a global database, creating a vast and constantly growing collection. Over time, patterns and correlations will begin to emerge from this enormous database. We will notice that interstellar comets from one region of the galaxy systematically differ in their chemical makeup, for example, with a prevalence of carbon. In another region, we might find that comets contain more water. These observations will open new horizons for understanding. Why does this happen? Perhaps, in areas rich in carbon, smaller mass stars formed predominantly, influencing the chemistry of planetary disks. Conversely, in regions abundant in water, increased supernova activity may have led to gas enrichment with oxygen and other elements. The first 3 atlases are just initial steps toward creating this vast library. Each entry is a data point, a small part of the overall picture. But this is only the beginning. In this context, even an element like nickel, though in small quantities, serves as a reminder that each data point has its own unique story. Every elemental ratio is a clue, a kind of key to understanding the history of this interstellar body. And if we analyze these clues patiently and carefully, we can read an entire book of its history, and along with it, piece together the collective chronicle of our galaxy. Part 13 is dedicated to the invisible population of space. Over the past 7 years, only 3 interstellar objects have been discovered, 2, Boris, and 3, Atlas, confirming their rarity but also indicating that they are not so uncommon after all. Overall, these objects are few, but their presence already allows us to draw important conclusions and conduct statistical estimates. For example, astronomers, based on the data obtained, have calculated that at any given moment, several such interstellar bodies are likely orbiting around Jupiter. They are small in size, dark, moving very quickly, and often remain unnoticed. Currently, in the southern part of the world, in Chile, a unique astronomical observatory is under construction, bearing the name of the renowned American astronomer Vera Rubin. This observatory is designed for comprehensive scanning of the entire visible sky at regular intervals, enabling the collection of images of nearly all known astronomical objects within the range of faint and very faint luminosities. Its main goal is to detect and monitor various celestial bodies that move or change over time, whether asteroids, comets, supernovae explosions, or interstellar objects entering our solar system from beyond its boundaries. According to preliminary estimates by specialists, the new observatory, named Rubin, will be capable of detecting approximately one interstellar visitor per month, and possibly more. This means that over a year of operation, it could discover at least 12 such objects, and over 10 years, more than 100. This statistical sample will give us a unique opportunity to start obtaining real, data-based insights into the composition, origin, and diversity of interstellar bodies, as well as understanding which types of objects are most common in our galaxy and how they move through space. An important component of this system is also a network of radio telescopes covering about 1 square kilometer, being constructed in Australia and South Africa. Radio observations allow for the detection of even the faintest molecular emissions from comets and other cosmic objects. Thanks to technologies like the Square Kilometre Array, SKA, we will be able to discover interstellar comets that often remain undetectable by optical telescopes, especially if they are inactive or located in distant regions of space. Additionally, space-based ultraviolet and infrared telescopes will monitor active comets that do not emit in the visible range but radiate in ultraviolet or infrared wavelengths. Each new device and method expands our capabilities to detect faint, fast-moving wanderers, interstellar bodies passing through our system at speeds reaching tens of kilometers per second relative to the Sun. This complicates the task, because once an object is detected, it is necessary to analyze its orbit as quickly as possible, assess the prospects for further observations, and develop plans for its study. However, often by the time we manage to notice and evaluate an interstellar visitor, it has already left the observable zone, disappearing into the depths of space. For example, the object named Moi was discovered just as it was beginning to exit the observation zone, and before it could be examined in detail, it vanished, moving far beyond visibility and becoming too faint to be redetected. In contrast, scientists managed to record 2 other interstellar objects approaching our system, so-called ice bodies or Boris. Their discovery provided scientists with months for study, which was invaluable. Telescopes around the world were directed at these objects, collecting spectra, measuring their light curves, and conducting detailed observations, which provided a wealth of data. It was an ideal scenario: timely detection, thorough study, and data collection. It is also worth mentioning that we identified 3 other interstellar objects quite early, so-called Oumuamua-like objects, allowing us to prepare in advance for their investigation. We obtained good data, however. Soon these objects will reach perihelion, the closest point to the Sun, complete their orbit around the star, and once again plunge into the darkness of space. If we fail to intercept them, they will disappear from view forever, leaving behind only a few traces. Today, ideas have already been proposed for special space missions to intercept such interstellar objects, not just to detect them but also to establish active contact. Nowadays, it seems possible to study complex organic molecules that previously appeared inaccessible for analysis without direct laboratory presence. Thanks to the development of new technologies and methods, scientists can search for and examine amino acids, key components of prebiotic chemistry, molecules that could serve as the raw material for the emergence of life on other planets. Moreover, with incredible luck, there is even a chance of discovering such molecules in fossilized microbes preserved in ancient rocks, which would open new horizons in understanding the history of life in the universe. Even if we do not manage to find living organisms or their remains at this moment, such research will provide invaluable information about the chemical composition and properties of alien planetary systems, as well as the processes occurring within their interiors and atmospheres. Every molecule discovered, every mineral, every isotope found on other planets or in interstellar space could become a crucial clue revealing the secrets of the origin and evolution of cosmic bodies. Some scientists are already developing plans for such missions, creating concepts, and forming budgets. All of this is not science fiction of the future but real steps in modern engineering and science. These ideas and projects are not just dreams, they are feasible tasks requiring complex, multi-stage engineering work, which, despite its difficulty, is entirely achievable. Within the next 50 years, and possibly even 100, humanity will be able to develop systems capable of cataloging hundreds of interstellar objects, visiting and studying a dozen of them, and also delivering samples from half a dozen such bodies for more in-depth analysis. Thanks to these studies, we will have the opportunity to gain a comprehensive understanding of the diversity of galactic comet populations, the structure and chemical composition of planetary systems, and perhaps even the prevalence of elements that serve as the building blocks of life throughout our galaxy. The Tria Atlas project is nothing more than a preliminary glimpse into the limitless possibilities that open up before us thanks to the development of interstellar research. This overview shows that interstellar comets are not rare or unique objects, but rather quite common phenomena scattered throughout the galaxy. They are not exceptional or accidental; on the contrary, their widespread presence indicates that they carry important information essential for understanding the processes of planetary system formation, their chemical makeup, and possibly even the distribution of life. This invisible population of interstellar bodies, hidden in the dark depths of space, roams there, awaiting the moment when our technology will be able to detect and study them. And we will, sooner or later, achieve this. Gradually, one after another, we will begin cataloging these objects, studying their composition, properties, and dynamics, piecing together parts of the puzzle that will explain how planetary systems form, how chemical processes vary across different regions of the galaxy, and perhaps, only perhaps, how widespread life is in the universe. Part 14. When we sum up all these anomalies and analyze them, the time indicates approximately half a second, which points to the need to scale down our perception. We need to look at the big picture, because the Tria Atlas is not the only strange phenomenon occurring in modern astronomy. In reality, there are many more mysterious and inexplicable phenomena than initially seem. Among them are mysterious radio circles and enigmatic rings of radio emission, the origins of which remain unknown even after numerous studies. Fast radio bursts, or millisecond pulses of radio energy coming from distant galaxies, are another example of unique phenomena whose mechanisms are yet to be uncovered. It is also worth mentioning the star Tabi, which exhibits strange patterns in its dimming, apparently caused by unusual cosmic structures or objects. Gravitational wave detectors constantly record processes involving the merging of massive objects such as black holes and neutron stars, providing us with unique information about the most extreme events in the universe. At the same time, radio telescopes continuously scan the celestial sphere, collecting data on millions of objects located at vast distances from us. As a result of this ongoing observation, we face an enormous volume of information, from which it is sometimes impossible to extract all the important details. The more data we collect, the higher the likelihood of encountering unusual phenomena, anomalies that stand out sharply against the general background. When looking at billions of observed objects, even with a very low probability of strange or unusual events occurring, say, only 1 in a million, such objects may exhibit signs of something extraordinary. In essence, we could discover thousands of such anomalies. Most of them are likely to be the result of technical errors, data artifacts, or misclassification. However, among them, there may well be genuine, unique phenomena that will require significant time and effort to study. In the era of modern technology and observations, anomalies often turn out to be events that precede existing theoretical models. We discover new objects and phenomena faster than we can explain them, which is both exciting and dangerous. This is a fascinating process because each new unusual case could become the starting point for discovering new physical laws. For example, the discovery of pulsars, gamma-ray bursts, or gravitational waves began with a series of inexplicable observations that initially appeared to be mere anomalies. At the same time, these unusual signals are potential sources of breakthrough knowledge. They offer the opportunity to expand our current understanding of the universe, uncover new physical mechanisms, or even open doors to unknown areas of science. However, such anomalies also carry risks. Hype cycles driven by hypotheses about possible revolutionary discoveries can spiral out of control, leading to waves of speculation and unfounded assumptions. Each anomaly is often presented as a potential breakthrough capable of radically changing our understanding of the world. Sometimes, these phenomena are linked to extraterrestrial megastructures, traces of warp drives, wormholes, or interactions with dark matter. These ideas generate intense reactions in the media and captivate the imagination of the general public. Yet, in 9 out of 10 cases, behind an unusual signal lies something much more mundane. Most often, it is dust clouds, random noise from equipment, or errors in identifying known objects. Such disappointments pose a danger: the loss of public trust in scientific discoveries and forecasts. People begin to perceive reports of potential extraterrestrial civilizations as fantasies, and scientists as those engaged in empty speculation. This was particularly evident in the case of the mysterious star Tabby, known as KIC 438. When the hypothesis that a massive alien-made megastructure was orbiting it made headlines and became a topic of discussion on social media, public interest reached its peak. Many believed in the possibility of such structures, as the idea seemed exciting and revolutionary. However, later observations, especially those showing the dependence of dimming on wavelength, convincingly indicated the presence of dust rather than solid megastructures. This scientific interpretation sparked conflicting reactions. Some accepted it as the definitive explanation, while others continued to believe that scientists were mistaken or hiding the truth. Yet, even after all this, interest in the mysterious star did not fade, as the dust-based explanation does not fully account for all its peculiar behaviors. Longer-term monitoring reveals a complex, evolving dynamic characteristic of an unusual star, which may be surrounded by a disk of debris left over from planetary collisions or other cosmic impacts. There are hypotheses suggesting that this star is doing something we have not yet understood. An anomaly related to nickel prompts us to consider the complex relationships between the chemistry of metals and celestial bodies, processes that we have largely ignored or taken lightly, since our observations of comets show extremely weak or non-existent metal emissions. The influence of predominantly carbon dioxide in these objects raises doubts about what protoplanetary disks look like in other star systems, which in turn questions our traditional ideas about planet formation and the initial conditions in the early universe. If we combine many such unusual observations, certain patterns may begin to emerge, hidden behind apparent chaos. There are hypotheses that mysterious radio angles and fast radio bursts, sometimes detected in space, may be interconnected, as both could be manifestations of energy outflows from galactic centers or other massive structures in the universe. Interstellar objects like Oumuamua or 2I, Borisov may represent different populations with unique mechanisms of origin and development, indicating the richness and diversity of processes in the cosmos. The vast and diverse, transient zoo of astronomical phenomena seems to tell us something more fundamental about the very nature of the universe's energetic richness. Or perhaps all of this is just coincidence, related to our recent technological advances that now allow us to detect such mysteries precisely at this time, in the era of modern technology. It is possible that these phenomena are not individual features unrelated to each other, but simply the result of finally learning to notice and record them, thanks to tools capable of revealing new horizons. Any hypothesis and any answer in such a situation are valuable, because it is important to maintain both skepticism and genuine wonder at the unexplained. We can rejoice in the appearance of a new anomaly without claiming that it completely overturns the laws of physics or changes our understanding of the world. It is possible to explore the potential opportunities that it opens up without blindly committing to them, while remaining open to changing one's perspective as new data and more precise research emerge. Clear and honest scientific communication is especially important in such cases. When scientists and journalists discuss new discoveries related to, for example, the 3 atlases, they should clearly and honestly acknowledge, this comet behaves unusually. We are considering several possible explanations. Here is what we know at the moment. It is not an alien intervention, nor a violation of physical laws, but rather a complex and mysterious object whose behavior raises questions. We are not trying to create sensationalism for clicks or hype, and honesty in our assessments helps maintain trust. This approach helps prevent any anomaly from turning into a sensational story that quickly becomes noise and disappointment when it turns out that everything is much simpler and more mundane than it initially seemed. The main thing is not to stop reporting on new observations but to maintain a balance between caution and curiosity. It is important to honestly acknowledge uncertainties, propose multiple hypotheses, and calmly update information as new data become available. The public should be regarded as mature and reasonable people capable of understanding and accepting the complexity, multifaceted nature, and uncertainty of scientific processes. Most people understand that science is a dynamic and evolving mechanism, and the answers we provide today are merely a step toward deeper understanding. What remains unknown for now is not a flaw but a natural part of the scientific process. The 3 atlases are just one of many mysteries contained in the stack of data. It is important to remember, this is not definitive proof of anything, but merely an important aspect of scientific inquiry. It's part that demonstrates how exciting discoveries can be. It is a source of wonder and inspiration, an opportunity to learn and grow, opening new horizons for exploration. And let any of these objects be in the depths of space, among the endless expanses, a mysterious comet appears, seemingly from nowhere, pouring water into the vacuum of space. And this water, instead of quietly dissolving and disappearing, flows into the cosmic void where it is not meant to flow. Glowing with an unusual green hue caused by the presence of nickel and cyanide, it attracts attention with its brightness and mysterious aura. This shimmering effect seems intentional, as if someone deliberately turned the light sources on and off, creating an impression of a purposeful play of nature. Its composition includes chemical compounds originating from other star systems, raising the question, where did these materials come from and why are they here? Perhaps this comet is a testament to a different era in the history of our galaxy, a time when processes and conditions could have been significantly different from today. Does it live in the literal sense of the word? Perhaps in a poetic, figurative sense, yes. It seems alive because it is dynamic, changing, responding to environmental variations as if it possesses its own will. However, from a scientific perspective, all its behavior can be explained by the laws of physics and chemistry, since it is active when it should be at rest, not in motion or growth. The behavior of this mysterious cosmic object appears purposeful, as if it has some internal goal. But in reality, we understand that all its reactions are governed by the laws of physics and chemistry, not conscious intentions. Nevertheless, in a literal sense, this comet appears alive, because its dynamics and interactions remarkably resemble those of a living system. But then, what is the point of all this? Most likely, almost certainly, there are no signs of biological life in it. There are no metabolic processes, no reproduction or information transfer characteristic of living organisms. There are no indicators that, in the usual sense, would testify to the existence of life. The 3 atlases are nothing more than a rock covered with a layer of ice, which warms under sunlight, releasing gases and dust according to the laws of physics. Yet, it is precisely these laws that give rise to something astonishing, something we have not seen before and could not even imagine. In particular, the sublimation of water at such vast distances and under these conditions is a unique phenomenon. The presence of nickel in its composition, absent in iron, and the dominance of carbon dioxide in its atmosphere, are notable. The behavior of this comet seems very complex and diverse, suggesting an unusually intricate internal structure or an unusual ice composition. Each new observation adds another layer to this mystery, making it more fascinating and enigmatic. So, what does this structure actually represent? The most probable explanation is a natural origin, that the 3 atlases is a typical comet formed under conditions significantly different from those that existed in our solar system. Perhaps it originated farther from its star, in colder regions of space where carbon dioxide ice prevails over water ice. Maybe its parent star had an unusual chemical composition, leading to such a strange ratio of metals and elements. Or, over billions of years, cosmic weathering in the interstellar medium altered its surface, resulting in a unique chemical makeup. An intriguing hypothesis involves metal organic compounds. If nickel is part of volatile compounds, such as nickel-carbon complexes, This could explain the observed emission features. Such a scenario would require specific chemical conditions at the time of formation, but there is nothing impossible or incredible about this. These are merely unusual, yet plausible, scenarios. The origin of the thick layer of ice covering the comet appears convincing. If we assume that 3 atlases have existed for around 7 billion years, and if isotopic traces indicating earlier epochs of galactic chemistry are preserved within it, then it is possible to suggest that it bears signs of very ancient processes. You can imagine how unusual chemical traces, so-called markers, might be embedded in the spectrum of an interstellar object. These markers are a kind of unique signature that would immediately catch the eye of anyone analyzing the spectrum. Their presence in spectral data would allow us to detect and record the very signs indicating potential artificial origin or an unusual nature of the object. And if, during the approach of this body to a star, natural processes such as sublimation caused the acceleration and release of these markers into space, their detection would become possible through observation. Of course, all this is pure hypothesis, and at present, we have no direct evidence that such markers are present or can be detected. However, it is important to note that if we ever encountered an artificial interstellar object, it might initially appear as an ordinary comet. Such an object could look quite strange, with an unusual shape or behavior, but at first, it might be mistaken for a natural body until more thorough and in-depth investigation is conducted. It could resemble, say, a strange, so-called three-eyed comet, an unusual, impressive sight that would immediately attract scientists' attention. In other words, this could be called the 3-eyed Atlas, a metaphor for an unusual, mysterious figure that raises questions and doubts. Likely, such cases are rare and almost certainly unique, but the very fact that we are asking this question and considering such possibilities speaks volumes. It indicates that this hypothetical comet is so extraordinary and enigmatic that it can expand the boundaries of our imagination, making us ponder what might be possible in space beyond our usual notions. These thoughts compel us to consider scenarios and possibilities that we typically dismiss or deem unlikely. And perhaps that is the true value of such reflections, not whether this object, for example, the 3-eyed Atlas, is natural or artificial, or whether its chemical composition is so unusual that it could fundamentally change our understanding of cosmic bodies, but that it prompts us to think. It pushes us toward doubt, re-evaluation of previously established assumptions and beliefs. It reminds us that the universe is much larger and more wondrous than our small corner, and that over billions of years of its existence, trillions of star systems and vast expanses of space have given rise to many mysteries that are only beginning to be uncovered through our exploration. That is why investigating the chemical composition of interstellar objects is an important and exciting task. Each such visitor from the depths of space is a challenge to our existing models, theoretical assumptions, and normal perceptions. These challenges are, in essence, the source of our growth and development as scientists and researchers. Many scientists and specialists have already questioned our understanding of the nature of comets. For example, the study of an object named Boris forced us to reconsider our assumptions about the presence of carbon monoxide in its composition. And what Atlas represents is a challenge to everything we knew about chemical balance, metal behavior, activity distances, and various components within such bodies. All these discoveries remind us of the need to continue observations and analyze each new approach. We must carefully monitor the object approaching perihelion, the point closest to the Sun, and record everything happening around it. Spectra need to be measured, light curves constructed, gas production rates tracked, the dust-to-gas ratio observed, new emission lines searched for, and analyses conducted to see if iron finally appears in the spectrum or if the nickel anomaly persists. All of this is important for comparing the data obtained with existing models, and sometimes, questions themselves are more valuable than the answers that follow. After all, it is questions that mark the beginning of any genuine research, any quest for truth and understanding. In the depths of cosmic mysteries surrounding us and in the unexplored depths of the unknown, questions serve as the starting point for our reflections and discoveries. Imagine, one day, an unusual messenger arrived, an atlas of Tria, delivered from distant light years through a journey spanning over billions of years, carrying a message made of water, nickel, and cyanide. We did not request this message, we did not expect its appearance. We do not even fully understand what it wants to tell us or what secret message it contains. But despite this, we listen to it. We observe its manifestations carefully. We strive to understand its meaning. And it is precisely in this process of discovery, in our constant effort to unravel what lies behind this message, that we find something very important. Something that seems almost alive within this entire story. There is nothing more than the mystery of the comet, something greater, our curiosity and wonder. We, humans, trying to grasp a little of what has come from the infinitely distant, attempt to decipher a letter from another world, from those remote depths of space. The universe tirelessly continues to send us such messages. Space postcards, messages like bottles cast into the sea, and guests from the darkness. All of this reminds us that we live in a vast, ancient, and inexhaustibly rich universe. This universe will forever surpass our understanding. It will continually surprise us with new discoveries and secrets hidden within its infinite expanses. The three atlases are one mystery among the endless sky, one comet among millions. But now, this mystery has become ours. And regardless of what is concealed behind this piece of ancient ice or something greater, whether its secrets easily uncovered or those that resist for decades, we will keep searching for answers. We will keep asking questions. We will keep listening to what the universe is trying to tell us. Because that is what it means to be human. To gaze into the night sky and not look away. To demand answers, even when it seems the universe is silent. To find wonder in the spray of water molecules moving at 40 kilograms per second in the green glow of nickel, which should not be there. This is all part of our desire to understand. For we see something strange and wondrous, even if it's just molecules, and we seek meaning, even when it's hidden behind miles or centuries. We are children in this enormous cosmos. It is unimaginably vast and boundless. But it is precisely between us and this immeasurable emptiness, between our telescopes and distant comets, between our questions and possible answers. That's where the conversation lies. A quiet, slow dialogue stretching across centuries and light years, captured in photons, spectral lines, and orbital motions. The three atlases spoke, we heard their messages, and we still remain attentive to what they will say next.